Hello, welcome back. The title of this lesson is Pure Substances, Elements and Compounds, and also an introduction to the periodic table of the elements. So we have a lot to cover here, but it's absolutely foundational bedrock material that everyone has to understand in order to take any steps in chemistry. The good news is it's actually really interesting and really not difficult at all. So what we're going to do, first of all, is introduce the periodic table. We're not going to do a deep dive into it right now, just the introduction so you can get the framework of what it is. And we're going to talk about the elements on the table and how these elements join together in a little more detail to form compounds, and just learning the difference between elements and compounds and molecules so that you got to get the vocabulary going, okay? So here is my version of the periodic table. Now, whatever class you were taking, in the textbook that you have, open it to the front or the back. There will be a periodic table. I encourage you to open your book to a periodic table so you can follow along with me. And if you don't have a book, just go on the internet and find a table, and you can easily follow along. This is something that's free knowledge. You can find it anywhere. So there's nothing special about this table. It's just the one that I was able to print out, and it's nice and clean, okay? So what do we have? Periodic table of the elements. Everything you know about in the universe, everything you've ever encountered, the air you breathe, the wood that you burn for warmth, the metal that your car is made of, computer chips, anything that you can possibly think of made of matter is made up of one or more of these elements on the periodic table, which are bonded together in different configurations. You can think of it like building toys, like Legos or something, where the elements are the individual building blocks, and they all have their own character. And when you combine the blocks in different ways, you can create completely different substances with completely different properties. Even if you make them out of the same materials, if you structure it differently and build it differently, like you can with Legos, then you get totally different, essentially totally different, substances. So we have kind of a blow up of what it looks like, one of these little squares here. So in every one of these squares, we have the name. In this case, it's mercury. And then we have underneath that a number in bold here, every one of these. We have the atomic number. We're going to talk a lot more about the details later. But the atomic number is how many protons exist in the nucleus of the atom. The atomic number is what makes all of these elements different. All of these elements, the main difference they have is the number of protons in the nucleus that defines the character of the element. So Mercury, for instance, has 80 protons in its nucleus, in the center there. Then we have the symbol Hg. Notice Hg doesn't look anything like the word mercury. That's because a lot of these symbols come from the Latin words that were originally used. So Hg is from the Latin word for mercury. So some of them don't quite match, but most of them do. And then we have here, it's called average mass on this table. In your table, it might say atomic mass, or it might even say atomic weight. So this number down here is exactly what it says. It's the average mass of a sample of these atoms, or of one of these atoms. Now it's an average because in nature, there's slightly different flavors of these atoms. They're called isotopes. And so you have to kind of have a weighted average of all the different flavors out there to pick one number for the mass of the atom. Now that's getting into a little more detail. We're going to have an entire lesson on that. For now, just know that this number here is the number that we use for the mass of the mercury atom, or a mass of a sample of mercury atoms. And it's kind of an aggregate average of all the different flavors of mercury atoms, which we call isotopes, that exist in nature. It's a weighted average. All right, and we'll talk about the units and what the numbers mean a little bit later. And in this table, in the corner, we have something called the electronegativity. That has to do with how strongly the atom attracts or doesn't attract electrons. So we're going to talk about that a lot more later. You can pretty much ignore the electronegativity until we get to those lessons later. What I really want to do is to just kind of like broadly outline what this table is. So at the upper left, you have the element hydrogen. Notice there is a number 1 above the H, and the symbol for this is H for hydrogen, so that makes sense. And there's a number 1 here. This is the atomic number of hydrogen. That means there's only one proton in the center of a hydrogen atom's nucleus. And underneath here, 1.01 means the atomic mass is 1.01. We're going to talk about the units of atomic mass later. All right, and then this electronegativity, we'll talk a little bit more about that later. But what I mostly want to focus on is the symbol here is H. It has an atomic number of 1, which means 1 proton in the nucleus. And then as you bounce all the way over to the right of the table, we come to element number 2. So you would think that element number 2 would be over here somewhere, but the way you read the table is it goes 1, and then you have 2 over here, and then you have 3, and then 4, and then you skip over this white space. We'll talk about that later. Then we have 5, 6, 7, 8, 9, and 10. And then we come back over here to 11 and 12. And then we skip over here to 13, 14, 15. Now, the biggest question everyone has when they see this table is, why is it set up like that? Why do we have these big gaps? Why isn't it just a nice little table that's a rectangle? Well, that has to do with exactly the details of how the electrons that are orbiting the atom are, how they're filled. Electrons don't behave the way you might think. And they only fill, and when I say fill, they only occupy the orbits, quote unquote, around the atom in certain ways. And this table is really constructed based on how the electrons are filled. So if you see big gaps, it's because of the way the electrons are filled into the orbitals, we call them, which are something that we learn a lot later. So in the beginning, I just need you to kind of accept that you do read the table left to right, and any gaps that you see, and if it's stretched or looks weird, that just has to do with the way the electrons are filled, which I can't explain to you now because we have to kind of build our way up to it. But once we know how the electrons are filled, it's going to make total sense why there's a big gap right here and why there's so many of these elements here, but they're not really up here. That's all going to make sense when we can talk more about how the electrons in the atom are filled. Now, before we go any further, we're not going to do a deep dive into the atomic, theory right now, but I do want to kind of give you a little bit of a picture to start with, right? So you have a situation where you have a nucleus. The nucleus has a positive charge. And then you have an electron that's kind of going around this nucleus. Now, this is the picture that we tell everybody, that the electron on the outside is going around and around and around like a planet or a solar system. But we now know that electrons aren't like planets, okay? And that's the one thing I really want to really encourage you to think about early on. Yes, I'm going to draw these pictures. Yes, I'm going to lead you to believe that it's kind of like a solar system. But at the end of the day, in the back of your mind, I want you to remember, or just kind of keep it back here, that it's not like that. Electrons are not little balls that go around and around. They're not. Electrons are actually waves. And I do mean that literally. They are waves. In fact, all matter that you know and that you can touch, they're all waves. And that's really why quantum mechanics is so weird and so hard to accept, because it doesn't look like waves. But when you zoom in on stuff and you do experiments with electrons, they actually behave like waves. So it's really not orbiting, it's kind of waving. It's more like a wave that dances around this central nucleus. But for the purpose of visualizing it in the beginning, it's very helpful to think of it as something that orbits around like a solar system. So it's okay to think that. Just in the back of your mind, I want you to know that that it really isn't like that. And I'm going to lie to you now a little bit, but then we're going to change and kind of tell you what we really think things look like a little bit later. Now we have one proton in the nucleus. And because we have one proton in this nucleus, this is the hydrogen atom. Now, there's one proton in this nucleus, and there's one electron. Notice that you have a negative charge and a positive charge, +1, -1. So if you look at this atom from a distance, +1, -1, if you add them up algebraically, +1 and you add a -1, you get 0. So from a distance, the atom looks neutral. It doesn't look like there's any charge on a hydrogen atom, any net charge, because when you look from a distance, you have equal and opposite charges, +1 and -1. And all atoms behave like this. If you look at this chart, if you look over here at helium, right? This 2 in the atomic number spot, it means there's 2 protons. But all of these atoms are what we call neutral. They have equal number of protons in the nucleus and also electrons that go around the nucleus. And all of them look neutral because if you have equal and opposite number of protons and electrons, then from a distance, it's going to look like a neutral object. And that's why all the atoms around you, you don't feel, I kept telling you how the electric force is so strong. It's millions of times stronger than gravity, but you don't feel it because all the atoms around you have equal and opposite charges. So they don't look like there's any net charge. It's all canceled out with positive and negative, the proton being positive and the electron being negative. So there's, just by looking at this, you know that there's 2 protons in the nucleus, and therefore there must be 2 electrons surrounding the nucleus. If you look over here at phosphorus, you know from this number there's 15 protons in the nucleus, and therefore there must be 15 electrons surrounding the nucleus because a phosphorus atom is neutral, right? Before anything happens with chemistry, if you just have a neutral atom, it has to have equal and opposite numbers of protons and electrons. Over here, tungsten. This is in light bulbs, right? There's 74 protons in the nucleus of tungsten, and because of that, a neutral tungsten atom has to have 74 electrons surrounding the nucleus, in a cloud surrounding it. So in your mind, think of that solar system orbiting with all those protons in the middle and all those electrons going around, but just know that that picture is not really right, and we're going to revise that picture as we go on, but that's a good place to start. The other thing to tell you is I'm kind of leaving something out here. These numbers, 1, 2, 3, 4, and so on, they tell you the number of protons in the nucleus, but actually there's also, for most of these elements, there's also neutrons in the nucleus. So in the nucleus you have protons, which are positive, neutrons, neutrons have no charge at all. And then you have electrons surrounding. So neutrons make the atom have mass. I mean, it does contribute to mass, but they don't have any charge. So neutrons don't really participate in chemistry. They don't really, they're very important for nuclear reactors, and nuclear, when you try to break apart an atom or fuse an atom together, they're very important. But neutrons don't have really much at all to do with chemical reactions. In a chemical reaction, what we're mostly concerned with is we have these electrons on the outside of the atom, and these electrons are transferred and shared to the other atoms you're reacting with, and they can then form chemical bonds by the electrons on the outside cloud sharing and making new molecules and new compounds and new substances by joining these elements together in different ways. But since this is an overview lesson, the main thing I want to impress upon you with this periodic table is that the left-hand side of the table are the metallic elements. These are the metals here, and in fact these in the middle are metals. You see the nickel is here, the copper is here, the silver is here, the titanium is here, the gold is here, the mercury is here. And these are the metals here. And then over on the right-hand side, these are the non-metals over here. And you know that they're non-metals because you have things like nitrogen, oxygen, fluorine, chlorine, iodine. None of those things are metals. And so on the left-hand side, you have the metals, the metal side of the periodic table, and on the extreme right-hand side, you have the non-metals. And as you move this direction, the character of the elements begin to kind of change from being metallic to sort of being non-metallic. What do you think about when you think about metals? You think about something that can conduct electricity in most cases. You think about something that can conduct heat very well. You think about something you can pull into a wire and it's ductile, which means you can pull it into a strand, right? And what do you think about when you think about non-metals? You think about something brittle like carbon, right? Just like charcoal. If you think about charcoal, it just breaks, or graphite, it just breaks. You can't draw it into a nice long metal, right? What about, things like oxygen and nitrogen? Those are gases. And so, of course, they're not metals. So those are the characters of the elements on the right side of the table. Now, between the metals on the left and the non-metals on the right, notice there's this little staircase which sort of divides, the metal half of the table from the non-metal half of the table. That's what the staircase is. Now, the elements right on the boundary of the staircase, those are the ones that have some character of metals, but also some character of non-metals. So the elements near the staircase, the boundary of the metal and the non-metal, they would have maybe some ability to be drawn into a wire, maybe some ability to conduct electricity, but also maybe they have some non-metal character, like maybe they're not very strong, or maybe they don't conduct electricity as well as gold or some other, copper or some other metal like this. So let's look at the elements right on the border here, right? Well, the big one is right here, silicon, Si. And I know that you all know that silicon is the main element we use to build all of our computer chips. The reason we use silicon to build computer chips is because it's right in the middle between being a metal and being a non-metal. So we can build a circuit so that when we build things like a transistor in a computer chip, we build it out of silicon because it can conduct electricity when we want it to, meaning it can turn on, But then it can stop conducting electricity like a nonmetal when we also want it to, which means it can turn off. And all computers are built on being on or being off. And if you build something that can turn on and off really fast, then you can build you can build a computer, something that follows instructions. You can build a memory chip, and that's all built out of silicon. But we also build computer chips out of germanium in some cases, and even gallium in some cases. And these other elements here have their own uses as well. Notice that carbon is pretty close to the boundary as well, and carbon is mostly we're mostly made of water, but carbon is essential for life. So carbon's a very special element that has some character of metal, some character of nonmetal, and it can bond. Carbon can bond in ways other elements can't. They can make very long chains of compounds or chains of atoms, which your DNA in your body is a very long chain, billions of base pairs long, and that chain is how life can, exist. So that's the main thing I wanted to get at, kind of like impress upon you before we jump into the details of this class, is that we have a periodic table. It's ordered in order of atomic number. Here's 1 proton, we call it hydrogen. Here's 2 protons, we call it helium. Here's 3 protons, we call it lithium. Here's 4 protons, we call it beryllium. Here's 5 protons, we call it boron. Here's 6 protons, we call it carbon. 7 protons, we call it nitrogen. 8 protons, we call it oxygen. 9 protons, we call it fluorine, and so on and so on. And every time you see how many protons are in the nucleus of the atom, you also know that for a neutral atom, there has to be that same number of electrons surrounding the nucleus. And in the back of your mind, you also know the nucleus has some neutrons, which have no charge, but they do give the element mass. And so on this table, the mass is listed here, 10.81, 12.01, and so on, and we'll talk a lot more about the atomic mass a little bit later. Now, I want to turn your attention to something interesting, and that is if you keep going up this chart, you get to neon, which is a gas. Go back here to sodium, magnesium, and kind of keep going. Up here around element number 26 is iron, Fe. It comes from the Latin ferrous. And that's why the symbol for iron is actually Fe, but it's right here. It's not too far up the periodic table, really. There's a bunch of elements beyond iron. But the interesting thing about iron is we now know that these elements of the periodic table, the hydrogen, the helium, some of the lithium, these were formed in the Big Bang of the universe. And all of these elements up to iron were formed in the center of stars. So in the center of a star, you take the hydrogen, that's what was mostly available in the universe, and gravity compresses it together and it fuses together. Notice we have 1 proton in each hydrogen. You fuse them together, maybe you get something with 2 protons in the nucleus, we call it helium. And then gravity compresses the helium together. Each of those helium atoms have 2 protons, and you make heavier and heavier and heavier elements in the fusion inside of the star. This process continues, creating all of these elements up until iron. Then you can't make anything heavier than iron inside of a star. The mathematics just don't work out. You cannot have a star by itself with fusion continue to make heavier elements beyond iron. So the magic question is, the $1 million question, how did all the elements come about that are heavier than iron, that have more protons than iron? How did cobalt happen? How did zinc happen? How did silver happen? How did mercury happen? How did gold happen? How did any of these things happen? Well, we now know that those elements are only created in the supernova explosion of stars when the star dies, or if you have 2 special kind of stars called a neutron star, which are very, very, very massive stars, and they collide with each other and they basically explode. So only in cataclysmic explosions of the universe can any elements heavier than iron basically be made. So essentially, we now know that there's a cycle in the universe of stars being born, and then they die, and then they blow up, and then after they blow up, the gravity brings them together again, and they form a new star, and they blow up, and this happens over and over again, and as that process continues, we make heavier and heavier elements in the periodic table. So we know that our solar system has experienced several cycles of these stars blowing up and kind of re-coalescing again, because we can find these elements like gold and lead, and they had to have been involved in a supernova explosion. Now, let's take a look at the bottom of the periodic table. We have all these elements that you're familiar with: gold, mercury, lead, you've heard of those. And then we have kind of like two blank spots here. And down below the table, I've listed two long rows of very weird sounding elements. One row is called the lanthanide series here, and the other row is called the actinide series. All right, and I may be mispronouncing that, but you get the idea. And we have, these are fairly heavy elements here. And the way this table is constructed is that this entire two rows here fits inside of here and pushes this table off to the right. And this kind of fits inside of here. Now, the reason we draw these two rows down below is because if we draw the table all spread out, then I can't fit it on the page. So every textbook you'll ever see, you'll see those two rows at the bottom, but those two rows really do live here and push the table. The whole thing gets pushed to the right, but you can't print it on a page easily, so you always see it down below. And also, as you get heavier and heavier and heavier elements, especially toward the end, this table has up to element 118. That's the heaviest element that we know about now. But all of these very heavy elements are all radioactive, because when an atom gets so heavy that the nucleus is so incredibly huge, then the nuclear force holding the nucleus together is not really strong enough to hold it very well. And so occasionally a neutron will pop out and just leave, or a proton will decay into something else. And so then you have radiation, you have radioactive decay. All right, so the elements up at the top of the table, they're all very stable. They were created in the early universe and the early stars when they supernovaed. And then you have these other elements here in the middle, which were created as stars were born and as they had supernova and they died at the end of their life. And then you have these elements that we've only created in particle accelerators to bombard atoms together and to try to create them, but they're all radioactive, the heavy ones, and they only last for a nanosecond or some very small fraction of a second. So we have up to element 118, but you cannot hold a bucket of element 118. It's not stable. It's going to immediately decay into something less massive because the atom is so big, it just the nuclear force can't hold it together. So for the purpose of chemistry, we're mostly going to be focused on the top half of this table. Yes, you will have problems with some of these elements here, but most of the time we'll be dealing with these elements at the top. And when you deal with organic chemistry, we're mostly going to be concerned with carbon, nitrogen, oxygen, and hydrogen. Hydrogen is also very, very important. All right, so that's an overview of the periodic table. Let me make sure I have not missed anything. So we have about 100 elements. I told you that, 118 currently. Most of the heavy ones are totally radioactive. Ordered by atomic number, going from atomic number 1 all the way to atomic number 118. That means this heaviest one has 118 protons in the nucleus. There's also a bunch of neutrons in the nucleus, giving that atom mass as well. And then we talked about the atomic number for carbon and kind of like how to look at it at the chart there. And then we talked about some of these atoms come from some of these symbols on the table come from their Latin roots. Like a lot of them make sense. Like yttrium is Y for the word yttrium. Zr is zirconium for the word zirconium, right? It's chromium, Cr for chromium, manganese, Mn for manganese. But iron is from the Latin ferrous. That's why it's Fe, so that doesn't quite match. And there are other examples here. Copper. Copper, where's copper at? If I can find copper. Copper is right here. The symbol for copper is Cu. That doesn't really make a lot of sense. Cu comes from the Latin cuprum, right? Cuprum. And what's another example? Lead. Lead is right here. The symbol for lead is actually Pb. That doesn't make sense. It looks like peanut butter, but it actually goes with lead. And Pb stands for plumbum in Latin. So we don't need to write those down. We don't need to memorize them, but just know that the symbols on this periodic table, some of them come from the Latin roots. And the very last thing I want to talk about before we leave the periodic table is the main advantage of organizing the periodic table in the way that we have organized it over history here, in the modern form of it, is the following. This is an important punchline. When you order the periodic table this way, then columns, like this column, they have similar chemical properties. This column has similar chemical properties. This column has similar chemical properties. This has similar chemical properties, and so on. And the ones at the end, we call the noble gases, these have similar properties as well. So when we create the periodic table ordered by atomic number, spaced out in the way that it's spaced out, which is based on how the electrons fill in the electron shells, we're going to talk about that later, then you arrive at this table and every column has chemical elements or atomic elements that share chemical properties. In other words, those columns like to gain and lose electrons in similar ways, and that means we can predict their chemistry. a lot easier when the chart is organized like this. And we're going to talk a lot more about that later. But the next item that we need to really talk about in detail is the idea of a molecule and a compound. All right, so we know that atoms, a synonym for atom is element. If you hear someone say, hey, I have 37, or this atom on the periodic table is whatever, lead, and someone else says, hey, the element number whatever on the table is lead, the word atom and the word element, they basically mean the same thing. They're interchangeable, so that's the same thing. The periodic table of the elements, you could also call it the periodic table of atoms. That's fine too, because every box on that table is an individual type of atom, as we talked about a minute ago. Now, atoms can join together and form molecules. So they can bond, and when they bond either together or different elements bond together, we call it a molecule. Right? So let's give some examples of, molecules, right? So we have H2. Hydrogen, which is element number 1 on the periodic table here, symbol H with 1 proton in the nucleus, and this is its atomic mass, and it's in this column. You know it has similar properties to lithium, similar properties to sodium, and things like this. We know that if you take atoms of hydrogen and put them together, they like to bond together. You really can't buy a bottle of hydrogen that's just atoms floating around. They always want to bond together to make H2, 2 hydrogen atoms connected together by a bond. And why do they like to bond together? We're going to get into all that stuff later. We can't learn everything in the first lesson. Hydrogen likes to bond to itself. Oxygen, O2, likes to bond to itself. Chlorine, Cl2, likes to bond to itself. There's a few that like to do that. Hydrogen is one of them. But a molecule is when 2 or more atoms are connected and bonded together. So this is called a molecule. Right? And a molecule is anytime you have 2 atoms that are bonded together, right? Any kind, it doesn't matter, whatever elements you have, if there's 2 or more connected, we call it a molecule, right? Let's take a look at another example. What about Cl2? This is 2 chlorine atoms. The little 2 means 2 of them connected together. It's 2 or more atoms connected together, we call it a molecule, right? Now let's take a look at a more complex molecule, H2O. So this is 2 atoms of hydrogen and 1 atom of oxygen, and they are connected together and they form the water molecule. Right? Now, what I want to do is contrast that. These are very simple molecules because it's just 2 hydrogens connected, 2 chlorines connected. And this one's a little more complex. It's different atoms that are connected together, but it still forms a molecule, right? What about CO2? This is carbon dioxide, 1 atom of carbon and 2 atoms of oxygen connected together into a unit we call what? A molecule. So this is a molecule. And then I'll just do one more real quick, and that's the other one here. Instead of CO2, we just put CO. That's carbon monoxide. This is carbon dioxide. And you can see the difference is there's only 1 oxygen here. But still, they're connected together, and so they are a molecule. So you can see everything I have on the board here is a molecule because it's 2 or more atoms connected together. That's a molecule. Now, there's a subclass of a molecule. If you have a molecule with different elements that are like different elements on the table connected together, we call that a chemical compound. It's still a molecule. They're all molecules, but we call it a compound if the atoms in that molecule are different. So we can see that the elements in here are carbon and oxygen. Those are different. So this is also called a compound. It's just a type of molecule. These atoms are different. They're totally different. Carbon and oxygen, again, so we can call this also a compound. Right? Over here, water. We have hydrogen and oxygen, different types of atoms. We can also call this a compound. Right? Then we have Cl2. Here, we have 2 identical atoms of chlorine together. So this is not a compound. You see, a compound is just when the elements are different. This is not a compound. So this is just a definitional thing. To be honest with you, I don't even want to spend time on this because I think it's silly. It's just a definitional thing. They're all molecules. Just call them molecules. That's fine. But you might say, see in a book, the chemical compound CaCl2 has blah, 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 does blah, blah, blah. Compound just means it's a molecule with different types of atoms. These atoms are the same, so we don't call it a compound. These atoms are the same, so we don't call it a compound, but they're all molecules here. Now, the other thing I want to mention to you is there's different ways to represent these molecules. All right? We have the kind of like the symbol on the periodic table with the subscript. That just tells you how many of every atom is in these molecules. But you might see in your book them drawn in certain ways. Like the hydrogen, you might see as two hydrogens connected, you might see like them as little balls that are kind of like touching and kind of hugging like this. Right? So you might say this is a hydrogen, they're bonded together and stuck together like this. Right? This is chlorine. Chlorine atom's a little bit physically larger, so you might see like a physically larger ball, right? But again, there's two of them and they're connected together. Now you can also draw H2O in the same way, draw three balls. Like I guess you could draw like the oxygen bigger and the hydrogen right here and the other hydrogen here. So this would be like the oxygen, and then this right here would be the hydrogen, and then this right here would be the hydrogen. So you can draw it like that as well. But as I've been doing in the past, I've been trying to kind of teach you that the oxygen is connected to the hydrogens in a water molecule, and it's a bent structure like this. So you have a oxygen connected to hydrogen, oxygen connected to hydrogen. These lines are the chemical bonds that are between those atoms. We're going to talk a lot more about bonding later. You're not supposed to understand why they bond right now, but I'll just give you a clue. They bond because they're sharing electrons, and they're doing that because the electric force is so strong. That's what I keep telling you. Everything in chemistry comes down to the electric force is millions of times stronger than anything you have experience with. So everything that happens chemically is really always a result of how strong that thing is. So these things bond together because ultimately they share electrons, and that happens because the electric force is so incredibly strong. All right? And this bent shape, we're going to talk a lot about geometry. What does this look like? What does this look like? What does CO2 look like? Is it bent also? We're going to talk about all these, right? What does CO look like? What does that structure look like? We're going to talk about all of these in a future lesson. And then the other thing I want to talk about, as we're talking about now about elements and molecules and things, is that in general, if you take two or more elements and you combine them to make a molecule where they're stuck together, bonded, the properties of what you start with usually is totally different than the properties of the molecule you have after you connect everything together. Like the properties are totally different usually, right? So for instance, let's compare water, which is two hydrogens and one oxygen. Let's compare it just to hydrogen, and let's compare it just to the element oxygen. And let's talk about a couple of different things. Okay, at room temperature, water is a liquid. But at room temperature, hydrogen is actually a gas. And at room temperature, oxygen is also a gas. You're breathing it right now. So at room temperature, the two things that go into making up water are in a completely different state of matter, but somehow when you put them together, they form something that's in a liquid phase that can be poured, you can drink it, you could dissolve things in it. It is completely different character than what made up the molecule, and that's in general true. All right? Water in general has a boiling point, I'll put P for boiling point, of 100 Celsius. You all know that at sea level, it's about 100 Celsius to boil water. But the hydrogen that is inside of the water, the boiling point is negative 253 degrees Celsius. Very, very, very cold. And the oxygen is negative 183 degrees Celsius. So this is why when you look at rocket launches that use hydrogen and oxygen as the fuel and the oxidizer, we have to keep them really cold so they're in the liquid phase. Otherwise, you have a big tank of gas and you can't fit much in there. You have to have it as a liquid in order to fit very much in your fuel tank. And everything looks cold, like everything is frosted over on the outside. That's because those elements, hydrogen and oxygen, they're basically boiling at a really low temperature. They're turning into gas at a really low temperature. You have to cool it down really, really cold to keep it as a liquid, in other words. But yet, look at how different this is than once you make the molecule there. All right, and the last thing I will just say is that for hydrogen, it's a flammable gas, right? You can burn it, right? But oxygen by itself is not flammable, and water by itself is not flammable. I mean, you might think oxygen is flammable, but it's not. The idea of burning something is combining it with more oxygen. That's what burning is. Oxygen doesn't like to combine with more oxygen when you light it. but oxygen is required for other things to burn. So by itself, oxygen is not flammable. It doesn't burn by itself. You have to give something with the oxygen to burn. Hydrogen, of course, will combine with oxygen and burn. Water, we use it to put out fires. It definitely doesn't burn. So you can see that when you look at the properties of the things that make up the molecule itself is completely different character in almost all respects. The chemical properties, the physical properties, what it looks like, what it tastes like. I can't drink hydrogen. They'll kill me, right? It's not healthy for me to do that, right? Even too much pure oxygen can actually hurt the human body, but I'm encouraged to drink water all day long. And the same thing with other compounds and elements and stuff as well. The sodium in table salt, bad for you. The chlorine in table salt will kill you. But if you make sodium chloride table salt, yeah, you put it on your spaghetti and eat it. It's fine, okay? They have a different character once things are combined together. All right? Now what we want to do is solve a couple of quick problems. All right, we'll solve a couple quick problems. I think it's going to be a little easier to do it over here. And what I'm going to do is I'm going to list the element name. In the first case, it's sulfur. And you have to look up the symbol on the periodic table. Now you can use your own periodic table, or maybe you can follow along and look at this. So if we find sulfur, where is it going to be? Where is it going to be? I'm not actually even sure. Let's look around over here. Sulfur is right here. Sulfur is listed right here. It's element number 16. That means there's 16 protons in its nucleus and 16 electrons surrounding the nucleus. There's also some neutrons in there somewhere we'll talk about later. And the chemical symbol for the chemical element sulfur is S. So we'll put down S for sulfur. Okay? We'll just write these down and get a little bit of practice. Okay? What about gold? You might think G for gold, right? Let's see what it is. G for gold is G for gold. Let's take a look. Gold is right here. Gold is element number 79. 79 protons in the nucleus, 79 electrons orbiting around the nucleus. The symbol is AU. And of course, as we've said, that comes from some Latin word, which you could look up if you're curious, for the original word for gold. So AU. All right, just getting a little more practice. What about potassium? Right, what about potassium? You would think it would be P for potassium, right? Let's take a look. Here's potassium on the periodic table. It's element number 19, and the symbol is K. So obviously, it's not, doesn't make a lot of sense. Now, I will tell you that that's the other one I actually wrote down. So the symbol K for potassium comes from the Latin word kalium, which is what they originally called potassium. All right, let's take a look at D. D is copper, or I'm sorry, chlorine. What's the chemical symbol for chlorine? We look on the periodic table, and it's right over here. Here's chlorine. The symbol is Cl. You would think it's maybe CH, but it's not. It's Cl. So here's the chemical symbol, Cl. Next, we have copper. Okay, copper. And where is copper on our table? Where is copper on our table? Right here, copper, element number 29, and the symbol is Cu. Cu. Okay. All right, now we're going to do the reverse. Instead of giving you the name and you put the symbol, we'll do the reverse. I'm going to give the symbol, in this case, U is the symbol. What is the element? U. So all you have to do is look for U on this table, and or in the table that you have in your book. Where's it at here? It's down near the bottom, because I already know the answer, of course. It's cheating a little bit. Where is it at? Here it is. U is right here. And the symbol for, or the name of U is uranium. That makes sense. U for uranium. You all know uranium is important in nuclear reactors and things like that. And it has some radioactivity associated with it because it's such a heavy element. And so U is uranium. Okay. Next one. What about Ni? So grab your table out. See if you can find Ni. Okay, Ni is right here, and that's nickel. We'll write down nickel. Okay. Next, Na. One of the most important elements, actually. Na. Where's Na? Na is right over here, and actually stands for sodium. This is, again, a Latin word that started with Na, but it actually goes with the English word sodium. Sodium. Okay, very reactive element. If you put sodium in water, you'll see it spontaneously catch on fire. And there's a chemical reaction there we'll talk about later about that. All right, next, Al. Probably could guess what Al is. All right, let's take a look. Where is Al? Al is right here. That's aluminum. That makes sense. Al goes with aluminum. All right, and then our very last one for this, anyway, is Si. We actually talked about Si. It's a really important element. Si is here. That is silicon. Element number 14. 14 protons in the nucleus, 14 electrons orbiting around the nucleus. Of course, there's some neutrons in there as well. So this is silicon. Okay, so that was problem number 1. We're going to wrap up this lesson with a very short problem number 2. Now, it's the same sort of thing. I want to write something down on the board, and then together we're going to work through if it's an element or if it's a compound, and we're going to talk about if it's a molecule and things like that. So, problem number 1 here. Calcium chloride, which the chemical equation for, the chemical symbol for this is CaCl2. So 1 atom of calcium, 2 atoms of chlorine connected together, that's called calcium chloride. Is this thing an element or a compound? So remember, elements are all of these things. Those are the individual boxes on the periodic table. That's called an element. That's the smallest unit you can get where you can divide matter up and you have something that can't be divided any further and retain its character, right? If I divide down and get a bunch of silver atoms, if I try to break apart the silver atoms, then I just have electrons and protons in that, and it's not silver anymore. So those elements are the basic building blocks of things that we can build, you know, more complicated arrangements of. But we have different elements here, and so it can't be an element. And also, this is called a compound because it's different species there that are bonded together. So this is a compound, which is what we talked about on the board a couple minutes ago. All right, problem number 2. Sample of sulfur atoms. So if I order from a chemical supply house a bunch of sulfur atoms, is that a compound or an element? Well, you can look on the periodic table. We've already kind of looked it up because that was problem number 1 there. We know sulfur is one of the elements on the periodic table. Where is it? Right here. And so if you have a sample of just pure sulfur atoms, that's not a compound because a compound has to be 2 or more different kinds of things connected or bonded together. And if we just have a sample of sulfur atoms, can that be a compound? No, it has to be an element. So this is an element. Or you could just say it's a collection of atoms, right? And then here's our very last one. Now this is kind of a little weird. Let's take a look at something you probably haven't heard of, cytosine, right? Which is a part of DNA. So part of DNA, and it contains, it's a long molecule, and it contains hydrogen and carbon and nitrogen and oxygen. So is that an element? No, it can't be an element because these are all individual elements, and we're telling you that they're connected together. They're forming part of, it's not the entire DNA, a DNA strand or anything, but it forms part of a base of DNA, and it's made up of these multiple different elements. So this has to be a compound. All right. That wraps up this lesson. We have done a tremendous amount here. We have introduced the periodic table, which is already, it's like its own thing that you really have to focus on, right? And understand. And then we talked about more or less how the periodic table is organized, that it goes in order of atomic number 1, atomic number 2, atomic number 3, 4, 5. We got into a little bit of atomic theory, basically telling you that the number of protons in the nucleus basically determines where on the periodic table you are, and it basically changes from it makes one element different than the other, right? And so it's organized, this table, in terms of increasing atomic number, a number of protons in the nucleus. We talked about that every square in this periodic table has a name, right? An element has a name and also a symbol, and most of the time the symbol follows from the name, but sometimes it comes from the Latin, and so it's a little bit weird and a little different, but you just get used to it after a while. And then we said that the left-hand side of the periodic table is what we mostly call the metals. And as we move toward the right, we get to more and more non-metal character until finally we're over here at the gases, which are totally non-metals. And right here on the border with the staircase, we call that the transition region, or, where basically you have, the non-metals and the metals are kind of like in no man's land there. They have character of metals and non-metals, and we use those for computer chips, very important things, and also lots of other applications as well. And then we said that when we organize the periodic table like this, the columns on the table have similar properties. And I know that that's a little vague. We're going to talk a lot more about it later, but basically it means that these elements like to give and take electrons in a similar way. And it all comes down to the way the electrons are filled. Right now I'm just telling you that there's a bunch of electrons surrounding the atom, but they're actually filled in a very specific way. And the way in which they're filled is reflected in the table. And so things that are in the same column, they like to gain and lose electrons in a similar way, which means the chemistry of those elements in the same column are basically similar. So sodium and lithium actually act similarly, not exactly, but similarly chemically, and similar with the other columns as well. Then we talked about compounds and molecules and elements and just trying to understand the difference. Very important material. Some of these lessons in the beginning are long because there's a lot to get through. And if I slice it up into a million pieces, I'm going to lose a little bit of what I'm trying to say. I'd like you to watch this a couple times until you feel comfortable with what I'm saying, and then follow me on to the next lesson. We'll continue to build your skills. Learn anything at mathandscience.com.